Hello friends, in this video we will discuss about checking accuracy of physical equations. Make sure you watch Dimensional Analysis Part 1 and Part 2. Then go ahead with Part 3. Here we will cover topics: basic rules to check accuracy of physical equations, rules to find dimension of spatial functions, rules to check dimensional homogeneous or correctness of equation. So here is rules of addition. Only physical quantities of same dimensions can be added or subtracted. Suppose we have this equation where quantity B and C are being added. So this rule says dimension of B should equal dimension of C, because these two dimensions are being added here, so their dimensions should equal or same. Next rule says sum of quantities with same dimension is the quantity of same dimension. Means here two quantities B and C have same dimension and they are being added, so their sum, which is A, should have the same dimensions. Means dimension of A should equal to dimension of B and also dimension of C. Let's take an example. Here let's check the first rule. This is the kinematic equation. So dimension of U should equal dimension of A times T. So U is initial velocity. So dimension of velocity is Lt minus 1, and dimension of this quantity, this is A, that's acceleration, Lt minus 2, and for T is T. T is the time here. So this gave us Lt minus 1, minus 2 plus 1, minus 1. So we got the same dimensions here, Lt minus 1. Now the second rule, the sum should have the same dimension also, that's V here. This is the final velocity, so it would have the dimension of velocity, that is Lt minus 1. So you can see all the terms have the same dimensions. Let's take another example here. T minus mg equals ma. So let's check dimension of all the terms here. Here T is the tension force. So the dimension of force is mlt minus 2. So the tension force has the same dimension as the dimension of force. Now let's check the dimension of this term. For mass, it's capital M. And this G, gravitational acceleration. So all the acceleration, whether it is gravitational acceleration, linear acceleration or centripetal acceleration, they all have the same dimension as the normal acceleration, and which is Lt minus 2. So this will give us m L T minus 2. Now let's check the dimension of this term. For mass it's m, and for A it's acceleration, so we will use the same dimension Lt minus 2. So this will give us as well m L T minus 2. You can see all terms have the same dimension. Spatial functions are dimensionless. Dimensionless means they have no dimensions. If any quantity is dimensionless, its dimension is actually 1. So we say it has no dimension. So what are spatial functions here? Log is a spatial function. Log. Exponential means e raised to the power x, or any term having e like this. All trigonometric functions, which is sine theta or cos theta or tan theta. These all are spatial function and they have no dimensions or dimensionless. Let's take an example. Work equals Fd cos theta. If we have to find the dimension of work, then the dimension of force is mlt minus 2 and dimension of d is L. Cos theta is a trigonometric function which is dimensionless. So we will not consider it here. Just we will write m L square t minus 2. This is the dimension of work. Let's take another example of a spatial function. Here torque equals force times length times sine theta. Sine theta is dimensionless, so dimension of torque would equal to dimension of force times dimension of length, which is ml t minus 2 for force, and for length it's L, and sine theta has no dimension, so we will get ml square t minus 2. Here is a condition dimensionally homogeneous. This condition is for physical equation. All physical equations must be dimensionally homogeneous. That means they should be dimensionally correct. Homogeneous means they should have same dimensions, or all the terms in the equation should have same dimensions. There are two basic rules. If any equation follow these rules, would be dimensionally homogeneous or dimensionally correct. So first rule says both sides of equation should have same dimension, and also all the terms in the sum must have same dimension. If these two rules would be followed by physical equation, then that equation would be called as dimensionally homogeneous or dimensionally correct. Suppose this is the equation. So all the terms, that means this term and this term, this whole term, not one, this whole term and this whole term. So dimension of b times e raised to the power minus c should equal dimension of d plus e over f. Means this whole term should have the same dimension equal to the second term, and the both side of equation should have same dimension. So dimension of a should be equal to. Let's take an example. Here t equals 2 pi root m over k. We have to check if this equation is dimensionally homogeneous or not. So for that, what we will do, we will check the dimension of both sides of equation. Left hand side has only t, which is the time, so its dimension would be t. Let's check right hand side. It's 2 pi root m over k. 2 pi is a constant which is dimensionless. All the constants are dimensionless. So its dimension is 1, so we will not write that. Just write for m its mass. Square root means power is half. So m raised to the power half here, and divided by dimension of k here. K is the spring constant. So you know F equals to kx. We know this formula from spring. So K equals, if you rearrange it, K equals F over x, and F equals ml t minus 2. That's F is force here, and x is the length, so its dimension is L here. So we got K equals, L would be cancelled out, m t minus 2. We can plug in over here m t minus 2. Just keep in mind k is in the square root, so its power would be half here. So m raised to the power half divided by m raised to the power half, this power would be here, and then t minus 2 1 by 2. This power would be multiplication here. So these things would be cancelled out. Minus 2 we got 1 over t raised to the power minus 1. This 2 and this 2 cancelled out, and this would give us, when it would go on top, power would be positive, so we would get t. You can see left hand side and right hand sides are equal, so dimensions of both sides are equal. This equation is dimensionally homogeneous or dimensionally correct. If a physical equation is dimensionally correct, that does not mean equation is numerically or physically correct. In last page we saw that every equation should be dimensionally homogeneous or dimensionally correct. So that's a rule. But if we reverse the rule, like if a physical equation is dimensionally correct, then does not mean that that equation is actually correct. You know, t equals 2 pi root mk is the right equation, and this is the dimensionally correct also. But if we write the same equation t equals root m over k, this is not the right equation. But if you find the dimension of this equation, you would see the dimensions of both sides of equation are t, and so this equation is dimensionally correct, but this equation is not actually correct, or you can say numerically correct, or physically correct because this equation would not give you the right value of this time period. You need to add 2 pi here, only then this equation would give you the right value of time period. So, if a physical equation is dimensionally correct, that does not mean it's numerically correct also. Here is the question of the day. Solve it to see if you get the right answer. Answers are given below in the description box. If you have any question, please ask your questions in the comment box given below. Thank you.